Hello, everyone. Welcome to our bi-weekly QSI seminar. Today we have Richard Kueng amongst us, who will speak from Austria. And his talk today will be about using classical shadow formalism for quantum machine learning. And this is a work that Richard done a while ago when he was in collaboration with people from Caltech. Thank you, Richard.
Yeah, Maria, it's so great to be back in Sydney, even if it's only virtually. I am really excited about the opportunity to speak today and to see many familiar faces. And yeah, as Maria said, I'm going to talk about what we now call the classical shadow formalism. And this is joint work with John Preskill at Caltech, who many of you, I guess, will know and who doesn't need any introduction. But also I want to highlight the contributions of Robert Kueng, who is a very talented PhD student at Caltech. He actually has a classical machine learning background, but switched to physics for his PhD because he really wants to combine kind of quantum computing and machine learning. And towards the end of my talk today, I actually want to go a bit in this direction. And here, for a quick outline of my talk, I first want to give a motivation, which is, I think, very timely. I want to kind of look a bit on a high level at VQE problems, variational quantum eigensolvers, and I will try to argue that they come with an intrinsic readout problem that kind of motivates the need for very efficient ways to extract useful quantum information out of your quantum coprocessor in this case. And the classical shadow formalism is one rigorous way to achieve such a goal. You should really think of it as a very efficient quantum to classical conversion procedure that comes with rigorous performance guarantees. And once you have something like a quantum to classical converter, very similar to like what an analog to digital converter can do, you can start playing around with it. You can, for example, like start with a quantum processor, use your quantum to classical converter to wire it to a big, powerful classical computer on which you can do machine learning. And we are just like kind of realizing right now in ongoing work that I would like to share a bit towards the end of the lecture, that we actually can do surprising things when it comes to machine learning for quantum many-body physics problems. And their kind of access to a quantum device can make a real difference. And before I dive into medias res, let me encourage you to feel free to ask questions at any point. This is I'm going to try to keep it like kind of on a high level, introductory. And when you have any question, it's typically just interrupt me, just ask it. Chances are high that some other people also benefit from further clarification. And having said that, I'm a bit sad that I can't be in Sydney in person. So I have two screens so I can actually see your videos. And so I would appreciate it if you turn it on, but I also understand that you might not want to do that. But if you don't have problems turning on your camera in a recorded video, I would appreciate that a lot. Thank you very much. Okay, so without further ado, let me start with kind of the motivation I advertised, which is going to be the variational quantum eigensolver. And this is kind of really a hot topic right now, where we have like these near-term devices. But the idea is not new. It is 40 years old, and it goes back to Feynman's kind of like famous claim from 1981 that all of you undoubtedly know. And basically his vision was to kind of to build quantum computing architectures in order to compute or simulate other quantum systems. Because he really believed, and there's reason to believe that our supercomputers, which are ultimately classical processing devices, might be ill-suited to simulate quantum materials, for instance. And there's like many kind of like important examples where this seems to work. I think like one of them that is often cited is the electronic structure problem in chemistry, where you have like a not completely small molecule, but also not too large. And you want to actually find its exact molecular ground state energy. And because of quantum mechanical interactions between the electrons, this is a highly non-trivial problem. And the hope is that maybe a quantum coprocessor can help you achieve that. And like the paper that is usually cited in this context is kind of the Nature paper by Alberto, who used to be in Sydney, I think, until a couple of years ago. He's in Melbourne now, if I'm not mistaken. But like on a high level, these VQE ideas kind of try to solve ground state problems. And the ground state problem is not mathematically difficult. Usually you have like an energy function, a Hamiltonian, and you try to find the smallest eigenvalue. And that's not a difficult problem. What makes it difficult is that if you have a complicated system, the curse of dimensionality typically kills you. These Hamiltonians are exponentially large matrices. And so it's ultimately a scaling problem. And VQE kind of propose a hybrid strategy to try to execute a classical variational procedure that still finds you the lowest energy eigenstate, or like the lowest energy eigenenergy, by kind of starting with the problem you care about. And then you kind of encode it into the lowest eigenvalue of a synthetic Hamiltonian that is on your programmable n-qubit device, which is illustrated here. So maybe you have like a small, or like a not too small, but noisy device with n qubits. Then you can try to start with the problem you actually care about, like the ground state problem, use a Jordan-Wigner encoding or like some other encoding to kind of map the ground state energy you actually care about into the ground state energy of a Hamiltonian on this n-qubit device. But typically this Hamiltonian is not a native Hamiltonian to your device. It's really synthetic. And that kind of, it means that it's typically comprised of many different terms. Like in a Jordan-Wigner encoding, you would, for example, have Hamiltonian that is the sum of many Pauli observables. And then you still want to like kind of solve the ground state energy problem. So you kind of try to vary your ansatz function in order to find the ground state as a quantum state, but also the associated energy. And the way you do that in VQE is kind of, you have an ansatz function, a parametrization of your n-qubit states, maybe described by kind of circuit architecture. You kind of try to kind of start with a simple state, you apply your circuit, then you get an ansatz state, and you try to estimate the synthetic energy function, and maybe some additional information that then allows you to classically update, maybe with stochastic or optimization of stochastic gradient descent, kind of classically update the classical parametrization, the circuit of that kind of describes the next ansatz state, with the hope that it makes the synthetic Hamiltonian smaller. And then you iterate this procedure. So it's kind of really like an iterative algorithm that tries to find like kind of a classical value for synthetic ground state energy, but at each step you have your quantum coprocessor, and on a high level you outsource all these exponentially large linear algebra computations that you would need to actually do the normal variational principle to a quantum coprocessor. And you need it in each step of the iterative procedure. And this kind of imposes an immediate problem that I would like to call the VQE readout problem. Kind of each iteration, each update in your VQE procedure requires you to read out important classical information about your current ansatz state. Like the least thing you need is a good estimate of the current synthetic Hamiltonian energy that your current ansatz state achieves. And this comes with two problems. Like one of them I've tried to already allude to before. The Hamiltonian you kind of try to evaluate is not native. It's a synthetic Hamiltonian that is typically comprised of many simple terms. And so if you want to get that accurately, you might have to estimate many different simple Hamiltonian terms at once and sum the contributions up. And the second problem is just that quantum mechanics is a probabilistic theory, and strong measurements are typically destructive and probabilistic in nature. And so even if you're interested in just like kind of approximating one of these terms, you might need many repetitions in order to get sufficient statistics to get a good idea of what's going on. And these two kind of cost factors can add up. And I want to like kind of convey this idea in an actually concrete example that was done in 2019 by the Blatt group in Innsbruck. Like Rainer Blatt is very good at putting ions in a trap and building kind of like these type of quantum coprocessors. And they tried to use that to run a VQE algorithm to find low energy eigenstates, so steady states, not only ground state energies, of an interesting one-dimensional quantum electrodynamics model. I actually don't want to go into detail because kind of the first step they did is they took their one-dimensional quantum electrodynamics and used an encoding to map it onto a synthetic n-qubit Hamiltonian. And the encoded goal, kind of what you actually want to do on your quantum coprocessor then, is to kind of minimize a synthetic energy function that is comprised of two local terms. So kind of like each term in your synthetic Hamiltonian only acts non-trivially on 2 qubits, but it may not be geometrically local. And the total number of terms is quadratic in the number of qubits. But they had like a small interesting twist. They didn't only want to minimize kind of the energy itself to find the ground state. They were actually looking for low energy eigenstates. And so it's like a quick exercise for yourself. is to convince you that if you're actually not only looking for the ground state, but you're looking for steady states for energy eigenstates, then what you should actually do is to minimize the variance of your Hamiltonian. Because if you, in addition, assume that the underlying state is pure, then the variance of your synthetic Hamiltonian vanishes if and only if you are at an eigenvector at an eigenstate. But this kind of means if you compute variances of Hamiltonians, everything squares. And so they ended up minimizing an effectively 4 local operator whose number of terms scaled like the 4th power of the number of qubits. And in the end, they published a Nature paper where they did a proof of principle with 20 ions with a quantum coprocessor that had 20 qubits, but they actually ran the actual variational quantum eigensolver only for 8 qubits. And not too long ago, I was talking to the first author of this paper, Christian Kokai, and he told to me that the limiting factor that limited them to 20 qubits or even 8 was really the VQE readout problem. Kind of like in each step of their iterative algorithm, they had to kind of approximate n to the 4 different terms to sufficient accuracy to drive their VQE update. And that was ultimately the limiting factor for them. And in order to even go to 8 ions, they actually thought hard about how to measure these kind of different Hamiltonian terms because there's some additional structure. But the method they found still kind of scaled linearly in the number of qubits, and that was too expensive. It's kind of a bit like, I don't know how many of you actually work with semi-definite programs, SDPs. They are kind of like general purpose solvers, just as an example from the classical world, where we always say they are tractable because you can compute them in polynomial time. But the actual runtime also scales like a 4th order polynomial in system size, and that really limits you. And here you can really kind of see how different approaches deal with this kind of readout problem. And the naive technique is this green line. Here's a log plot. It really scales very poorly. Kind of what Innsbruck did is they came up with a smarter direct measurement procedure, which is kind of like this blue line. And the classical shadow formalism I'm going to try to explain now are kind of this red and the orange line. And as you can see, hopefully, like the x-axis is the number of qubits, the size of your quantum coprocessor. This kind of scales much more favorably in system size than the existing strategies. And I think here's a good point to stop and ask if you have questions about like the necessity to have a very efficient readout protocol in order to speed up VQE solvers and make them tractable. Any questions so far? Okay, very good. So I take it that you kind of see that there is a practical problem that kind of limits the capabilities of VQE and that we need a solution. And let me try to motivate how such a solution could look like by like abstracting the problem. And from now on, I want to kind of ask the following question: how do we efficiently estimate a huge collection? Like L is the number of terms we want to estimate, and it's much, much larger than 1, but of structured observables. And let's say structured, let's say like we want to estimate many low weight Pauli operators. By this, I mean many observables that are tensor products, and almost all of them are identity, but they might be X, Y, or Z on certain locations. And I will call the weight of the operator the number of not identity terms in your n-qubit Pauli observable. And when faced with such a question, like in my experience, typically you should ask the Simpsons for advice. And here's like one of my favorite Simpsons episodes where they kind of make fun of the infinite monkey theorem, which arose during the time Darwin propagated his theory of evolution. And for those of you who are not familiar with it, like Mr. Burns proudly shows Homer a room where he has 1,000 monkeys caged to 1,000 typewriters, and he's very certain that they will write the greatest book there ever was. And of course, Mr. Burns is right, because the probability that none of these monkeys will ever write a good novel is strictly smaller than 1. And so this is bound to exist, to happen at some point. And we can do something very similar. Let's just randomly sample single qubit Pauli measurements, like do randomized single qubit measurements with the hope, much like in the infinite monkey theorem, that we don't screw up completely. And that by just randomly assigning measurements, we will learn something interesting about each or about many of these Pauli observables at the same time. And this idea is not new at all. It kind of dates back to 2013 to a paper by Jens Eisart, but also the Innsbruck group has worked on that. And the intuition I now want to present is actually by Steve Flamia, who used to be in Sydney until very recently, I think. And in order to understand why kind of randomly sampling Pauli measurements for individual qubits is not a completely stupid idea, let us use a cartoon example and just ask ourselves, how should we efficiently estimate one of these low-weight Pauli operators? And here, like kind of each box is a qubit. And this is kind of the low-weight Pauli operator we're interested in. If it's white, it's identity, so we don't really care. But maybe at some point, this red could be a Pauli X. And maybe we want to measure X on this qubit and X on the next qubit. And now I'm proposing to like sample for each qubit a random Pauli measurement. And Paulis are incommensurable. So if I want to learn X for this qubit, I better measure X kind of like in my measurement. And now you can quickly convince yourself that the probability of kind of hitting, if I randomly sample each of these measurements, then the probability of kind of being compatible with this observable is 1/9. I have to be like correct for this qubit, which is probability 1/3. And I also have to be correct for the next qubit. I also have to measure X, which is 1/3. This is exponentially small in the support of the Pauli operator, in the weight, but it's completely independent of system size, right? Because it doesn't matter, like wherever the observable is identity, it doesn't matter what I'm kind of assigning. And that's the overall idea. And so kind of the probability of kind of by randomly sampling a measurement of hitting this particular observable is exponentially small in the weight of the Pauli operator, but it's independent of the total number of qubits. Right? And if we keep on like kind of sampling random Pauli strings for our measurements, then we also have to be careful to get like sufficient statistical information in order to get good approximations. And so we need like kind of the number of like random experiments we actually need is like 3 to the weight over the desired accuracy squared. That's just to overcome shot noise limit and get sufficiently good error bars. Okay. But now kind of the magic part comes, and the reason why it is useful to use randomized measurements. Let us now move on to the case where we have like many of these low weight Pauli operators that we would like to predict. And then like the arguments I just presented are valid for each of them independently. Like the fine structure doesn't matter at all. And then the power and magic of probability theory is going to tell you if you want to get like epsilon approximations for all L of them, the number of kind of measurements you need is actually logarithmic in the number of predictions you want to make. And that's ultimately because of exponential concentration. Kind of like if you kind of take more and more measurements, you kind of get these type of Höfting inequalities that are exponential tail bounds on the probability of not getting enough data. And so in the end, this allows you to just do a union bound over all the L different observables, or the all L different predictions. But if the L is there and you have like an exponential concentration, a log L factor suffices to overcome this. And in the end, this is also what you saw in the plot before. Kind of these like very, very slow kind of like rises in these curves are log-log functions. It's kind of a log plot of a logarithmic growth in the number of observables. Because this intuition tells you that if the number of predictions you have to make is like the 4th power of the number of qubits, the log of the 4th power of the number of qubits is 4 times the log of the number of qubits. And that's like a very small growth. Okay.
Can I ask? So do you need
please.
to make any assumptions about the relationships between the different observables?
No, that's exactly. I on purpose didn't do that because kind of like the different functions could be highly correlated, but I don't care. In the end, I just use a union bound that tells you the probability of like at least one bad thing happening is smaller than the sum of the probabilities of each bad thing. That's kind of like Boole's inequality. And so the probability of getting like at least one prediction wrong is smaller or equal than the sum over the individual failure probabilities, regardless of the correlations. And if I then have like an exponential bound for each of the failure probabilities, I get this log L scaling, regardless of the correlations. Chris?
Yeah, maybe I missed this, but what if you give me the white bar with the red dots and say I want to measure this Pauli string, why not just measure that one? Why do random measurements at all?
Yeah, that's a very good question. the case becomes interesting if this L is much, much larger than 1 and contains a lot of these low weight poly observables where you are not sure about the relations between them. One prediction is a bad example.
I see. Okay.
But like polynomially many,
yeah,
where you would have to like solve a difficult combinatorial coloring problem to like kind of first of combine them into different buckets of compatible observables that you measure independently then.
Right. So you only know that you're going to have to measure some low weight polys. That's all you know.
Exactly.
And you don't know which ones.
And plus, I actually don't know if I can solve kind of the pre-grouping problem efficiently.
Right. Okay.
Like if I give you a large collection of like low weight poly observables, it's a completely horrible problem to kind of like try to find compatible structure among them.
Cool. Thanks.
And kind of this kind of random tossing, like the infinite monkey theorem in a way lets you bypass the problem altogether by tossing coins and ignoring it. And in the end, you get actually something that is almost optimal.
So I think this is a simple question because we are doing independent measurement, right? And if we only care about low weight polys, then it's in some sense equivalent like overlapping tomography, which was so
yes.
cool. But I believe maybe one interesting question is like, what if we are caring about some of the high weight and some of the low weight in the combination? So what can we do?
I'm going to talk a bit about that later.
Okay, sure.
But there's like a standard technique that is called de-randomization, where you can like also kind of like take high weight poly operators into account.
That's nice.
So far, this is only kind of intuition. And again, this is not new. Kind of this intuition is from a Flamir paper. It's kind of just like designed to like tell you that randomized measurements are sometimes not as stupid as you might think, and compare favorably with smarter strategies. Okay, and kind of the classical shadow formalism we developed is kind of a rigorous framework to reason about these types of protocols. A kind of a rigorous framework that lets you kind of choose different randomized measurements and kind of tells you what types of observables you can hope to accurately estimate. Okay, and I want to be a bit brief there, but like we can abstract these ideas of random single qubit poly measurements by thinking of a more general procedure where we can create copies of our quantum state, and maybe then we can do a random unitary transformation that is sampled from a certain ensemble. Like this is now kind of like part of the measurement. What kind of ensemble do we have to choose our unitaries from? And at the end, we do a computational basis measurement in the single shot, and we obtain like a bit string of outcomes. Okay, that's kind of like the general framework we want to look at. And single qubit poly measurements would be a special case where like kind of your unitary ensemble would be a tensor product of single qubit unitaries, essentially, that kind of rotate you between the three bases. And now kind of the formalism starts to become a bit more concrete. Once you realize that you can actually view this entire procedure as a quantum to classical channel that kind of starts with a density matrix rho here, and then in the end to get something whose dimension is compatible with the density matrix, we can kind of form the classical post-measurement state, but we can form it classically on our computer. Like when we do this measurement, we know what the B hats are. We kind of know the bit string, and we also sampled a unitary at random, so we also know the unitary, and so we principle can build this density matrix, this post-measurement state on our classical computer. And now the important observation is that kind of this quantum to classical channel, we can compute the average thereof. Kind of like what this channel looks like if we randomly sample our unitary transformations from an ensemble and subsequently average over the selection, and then in addition average over the probabilities behind the bit strings that are defined by Bohr's rule in the end. And what we get if we just write this down is kind of a not too simple but also not too complicated expression that defines the average channel, and you can clearly see that it's linear in density matrix because Bohr's rule is linear in a density matrix. And it also features the unitary that we choose from our ensemble a total of 2 times and the adjoint a total of 2 times. And the observation we had was that kind of if this unitary ensemble is nice, you can efficiently and classically and analytically compute this type of average. For instance, if you have a Haar random unitary, or if you have a unitary 2 design, then this is a very reminiscent of a twirling formula, like it is used in randomized benchmarking, and you know how to compute these things. And once you know how to compute these things, you can also invert it. Like, we can't invert quantum channels on the quantum level, but if we just view them as linear maps, we can invert them on our classical machine. And that in particular implies that if we build first our post-measurement state based on the data we saw, on the single shot data we saw, we can apply the inverse channel classically on our classical computer and end up with with a row hat that's again like kind of a matrix. But this is now a random matrix that by construction reproduces the exact underlying quantum state if we take the expectation value over random choice of unitary and bit string outcome. And this is kind of the gateway to Monte Carlo sampling in a way, right? Because now we have a procedure that lets you do a simple randomized measurement and create a random matrix thereof that reproduces the actual density matrix, which we don't know in expectation. And we can do that multiple times and try to do Monte Carlo approximation of the underlying density matrix. And to make this a bit more concrete, let's really look quickly at this kind of like example of single qubit poly measurements, where our unitary ensemble U would be a tensor product of different single qubit unitaries. And if you look at this, we can again view it as a channel, but because every unitary is single qubit, there's like no cross correlation between first and second qubit. So on the post measurement state, everything factorizes into tensor products, because that's just collapse of the wave function for an n qubit device. And kind of like, because each single qubit unitary, each basis change is a 3 design, is kind of sufficiently generic, we can also compute these twirling formulas, and we'll see that this average channel is actually the n-fold tensor product of a depolarizing channel, just because everything is tensor product and factorizes nicely. And we can classically invert depolarizing channels. It's very easy. And so our snapshot would actually again be a tensor product where we kind of just take this, each single qubit contribution here, and apply the inverse of a depolarizing channel to it. And now we kind of have a way of rearranging the measurement data to get something that is still a tensor product and that approximates the underlying states in expectation. And that paves the way to Monte Carlo estimation. And if you then like keep on going, you can like kind of prove a very simple theorem. It's not that difficult in this case, that kind of tells you, if this is my Monte Carlo estimation for the density matrix, and I want to like predict a lot of different observables, right? Then I just replace the quantum state by the Monte Carlo average. And now the question is, how many Monte Carlo samples do I need to be like epsilon close in all of these predictions? And the answer, lo and behold, is the logarithm of the number of predictions times 4 to the weight, the largest weight of the observable, over desired accuracy squared. And that's kind of exactly the intuition I gave before with the single qubit poly measurements. Okay, and so kind of this kind of lends credence to the intuition I tried to give before. And it really tells you that if you're interested in predicting many low weight poly observables, for instance, then you should really do these single qubit randomized measurements, because the number of samples you need scales only logarithmically in the number of terms. And that is exactly where like kind of these slowly increasing curves in our VQE numerics come from. Okay, and now something interesting happened after we did that, because smarter people than myself got interested and like started to making their own contributions to this kind of framework for randomized measurements. And maybe the first thing I want to say is that kind of, if you take a different unitary ensemble, not tensor products of single qubit unitaries, but maybe global Clifford operations, a bit like what we would do in randomized benchmarking, then we also understand what happens. And this type of randomized measurements is well suited to predict different kinds of things. And this kind of, these random Clifford measurements have also been experimentally implemented and tested in a recent PRX quantum paper by a Russian group, and it works as intended. And then another thing that kind of was very interesting for the quantum many-body physics community is that with this ansatz, it readily generalizes to predicting polynomials. Because what classical shadows ultimately are about is to just kind of like always take, like write your functions as functions in density matrices, and then replace your density matrix with one of these Monte Carlo estimates with a head. And if you now want to predict a polynomial, in this case, for example, a quadratic polynomial, then you can write this as a linear function in the tensor product of the state with itself. And now you can replace each copy of rho with a different snapshot and average over all snapshots. And this will again give you an unbiased estimator for polynomials. And the beauty of Hoeffding's U statistics actually tells you that the number of samples you need for a polynomial to converge only scales linearly in the degree of the polynomial, not exponentially. So the extra cost of predicting more general functions is not as large as you might think. Another contribution that Steve Lamire, for instance, did is he recognized a hidden twirling structure that in principle allows you to run a randomized benchmarking protocol before you do these types of randomized measurements in order to learn important signatures about noise corruptions and effectively undoing them. So these ideas are also stable with respect to imperfect implementations under the same assumptions that randomized benchmarking usually works. More recently, there has been extensions to other physical systems, like people extended it to fermions. I think people try to also work on extending it to Bose-Hubbard models or Rydberg atoms. There's been a Bayesian interpretation, which I very much enjoyed reading about, because the way I tried to present these randomized measurements was very much in a frequentist sense, but there's also like a Bayesian approach to it. And last but not least, I want to address Nen Kueng's question from earlier, who rightfully pointed out that kind of these fair randomized measurements are not always a good idea. A very good example where they are horrible is quantum chemistry with a Jordan-Wigner encoding, because there your synthetic Hamiltonian is a sum of many terms, but most of the terms are actually poly X, whereas poly Y hardly ever appears. And if you're in such a situation, you would be stupid to do your single poly measurements in a fair procedure where you sample Y with the same probability as you would sample X. And so it can make a huge difference if you kind of locally bias the selection process to fit the structure of the observables you actually want to predict. And very recently, kind of we, inspired by these ideas, we developed a very general procedure that uses the technique of de-randomization from theoretical computer science to give you an efficient pre-processing algorithm that replaces all the randomized choices that you make by deterministic selections that are designed in a greedy fashion to maximize the probability of getting everything right. And this kind of also works. And so here's, I think, another good point to stop and ask if there are questions. Okay, everything is clear. Very, very good.
Can you, is there anything that you can say without pictures about the Bayesian interpretation?
Let's talk about this maybe offline. Okay. It's difficult without pictures, but very good question. Okay, but let me now kind of use the remaining time. It will be very brief to like kind of just pave the way that you can actually also use these ideas to do interesting things when it comes to machine learning. And the overarching idea is that kind of the formalism I conveyed to you allows you to kind of take a quantum system and get a classical fingerprint of the quantum system that is small enough to be tractable. It's like nothing is exponential, like kind of you can store it efficiently on your memory, you can manipulate it efficiently. And it's a rough sketch of your underlying quantum system, but kind of like it still seems to convey or like carry interesting information about the underlying system. And once you have such a quantum to classical conversion procedure, you can start combining quantum mechanical data preparation. For example, in a quantum many-body physics problem, you kind of can start to use a near-term device to try to generate quantum data for a certain training problem, and then use the classical shadow formalism to convey that into classical information and feed it in a classical machine learning procedure. And we looked at two concrete examples, which we think are difficult and interesting. And one of them is the task of predicting ground states, or more precisely ground state properties, based on just macroscopic descriptions of Hamiltonians. Like kind of suppose you have a classical description of a many-body Hamiltonian, like a two-dimensional Heisenberg model, then you would be interested in maybe learning how the ground state looks like, and not by computing it using DMRG, because DMRG is very difficult in 2 dimensions, but by maybe actually learning it. So like kind of your training data could be a macroscopic description of a Hamiltonian. Then your experimental friend uses his quantum platform to kind of produce the ground state of this Hamiltonian physically, and then create classical shadows, these sketches of this ground state for you. And then you could use these classical shadows for a classical machine learning procedure with the attempt to produce a new classical shadow, to learn how to produce new classical shadows of quantum materials you haven't seen yet. And we can actually rigorously prove that this works under certain physical assumptions, like spectral gap and these things. And another kind of machine learning question that we were very interested in is, can we use this type of quantum data generation to teach a supervised learning model to distinguish quantum phases, like a topologically protected phase from a trivial phase, like these things that we believe are difficult on a classical machine. And there the idea is very similar. We suppose that our training data is the classical shadow of a quantum state that belongs to phase A, associated together with a label that tells us it is in phase A, or it is a classical shadow of a quantum state in phase B, associated with a label that it is in phase B, and then we can use this label data to try to teach a supervised learning model in order when it gets a new classical shadow, it can then tell us if it is in phase A or in phase B. And long story short, we can also prove that this works under certain reasonable physical assumptions. And the numerics we did are even better than the theoretical predictions we could make. And for example, we looked at kind of how to learn to predict ground state properties of a random Heisenberg model. And this worked out like a charm. We really kind of trained it on random instances of ground states of the Heisenberg model, and it could predict the exact correlation values of a Heisenberg model it hasn't seen yet, with kind of very few data. And then we also did it a bit more interesting things with Rydberg atoms, and the phase classification protocols also work. But I wanna, maybe we can use the questions to dive into that, because I'm running out of time and I wanna wrap things up. I tried to kind of convey the idea that this classical shadows framework is a very powerful way of approximating quantum systems efficiently on classical computers. And this not only does you allow to compute functions you care about the quantum system, it can also serve as a more general quantum to classical converter that not only improves quantum classical algorithms like VQE, but it can also wire it together with a machine learning technique in order to do rigorous machine learning in quantum many-body physics that may benefit from the availability of quantum data. By this, I mean data that is non-trivially constructed based on a quantum computation. And with that, I'm at the end, and I want to thank you very much for your attention, and I'm happy to take questions.
Thank you very much, Richard. So yeah, I would really, so when you explain this approach, it seems almost as it's too good to be true. Because for ground state energies, we know that they are in the worst, this is a QMA complete problem, and in the worst case scenario, there are many things we can't do. So could you speak briefly about the definition of shadow tomography and basically where it falls if you try to...
That's an excellent question. And I want to use this opportunity to talk a bit more broadly about where the power of machine learning and AI in general can come from. And I think it is the power of learning from data. Like, for instance, kind of when you think about composing a musical piece, then this might also be a difficult problem, right? But a machine learning procedure might not be totally lost because it can learn from existing pieces of music. So kind of complexity theoretic arguments are very important. But when you want to model a machine learning model, a machine learning technique with computational complexity, you have to take into account that the data itself might have been generated from a process that is hard to begin with. Okay, so kind of if I just want to like purely talk about classical machine learning aspects, then you would think a classical machine learning procedure that runs in efficient time can only efficiently solve problems in P, not NP. But this is not quite true, because if I had an all-powerful oracle that, for example, gave me very powerful training data, then I could still use polynomial time algorithms to capitalize on that and potentially solve problems that are not in P. Now, you're very, very correct that, like, in general, these type of ground state problems in particular are even QMA hard. So we expect it to be difficult even for a quantum computer to solve that, but we don't claim that. We kind of, our theorems only work under reasonable physical assumptions, like a constant spectral gap, for instance. And I think the QMA hard instances don't have that. And the answer I would give you is that we kind of tacitly assume that we have an experimental friend who can take a classical input of a Hamiltonian and construct the ground state. That was a cool down procedure. And I would say for these QMA hard procedures, they just can't do that. And just by assuming that we have access to ground states of many body Hamiltonians, we implicitly avoid these kind of hard instances. But at the same time, I very much believe that there is instances where we could use a quantum device to efficiently prepare ground states that we couldn't simulate just classically. And so there's a window of opportunity where these types of procedures could be really more powerful than purely classical simulations, like we do for decades, and still not be in conflict with the complexity theoretic obstructions you rightfully pointed out to.
Thank you, that was a great answer.
And similar things are true with the classifying phases question. Like, we have an assumption for our theorem. Our theorem basically says everything works in polynomial resources, polynomial runtime and storage. But the assumption for distinguishing phases is that we have to assume that a nice underlying function that is capable of distinguishing the phases actually exists. And so when phase classification problems become difficult, it's usually at a critical point, and that's just very difficult to distinguish the phases. And so one of our assumptions is also not met, and our theorem doesn't apply.
Do we have more questions from the audience? Please just unmute yourself and ask Richard.
Richard, can you go back to the example that you spent more time on, the ground states?
Yes.
No, the ground states of no, in your machine learning.
Yes.
Yeah. So can you like walk us through what's happening here? Like,
okay, very good. Love to. What we consider is a 2D antiferrometric Heisenberg model on 25 qubits in this case. And so the Hamiltonian is defined by these coupling coefficients. And like there's one coupling coefficient for each edge in the square lattice. Okay?
Yeah.
And so this would be a Hamiltonian that is described by a number of classical parameters, the coupling coefficients, whose number is roughly proportional to the number of qubits. So there's no like exponential bottleneck. And the question is, given one of these classical descriptions, can you predict the ground state associated to the Hamiltonian, or more precisely, local properties thereof? That's the precise question. So kind of, and we do it in a training fashion. So like we assume that there's a training stage where we generate training data by randomly sampling these coupling coefficients, then producing a ground state. In our numerics, we use DMRG to do that, which limited us to 25 qubits. Kind of like compute the exact ground state of this Heisenberg model, and then convert it into a classical shadow description. Kind of like into these random bit strings. And that's your training data.
So that was done with the randomized or de-randomized?
Here we just did randomized measurements because we actually don't know what the relevant signature is. We just hoped for the best initially, that the classical shadows capture the right amount of information you need in order to learn to extrapolate from instances you've already seen to instances you haven't seen yet.
So you choose a large number of these random poly measurements, and then calculate the expectation values, and then construct the classical shadow from that.
Yeah, we never calculate expectation values. But kind of like for our first training data point, we sample one of these Hamiltonians at random.
Yeah.
Then we produce the ground state.
Yeah.
And then we do one randomized measurement, actually, only one.
Oh, okay. Right.
And that's our first training point. And then we repeat the procedure. We choose a different random couplings, construct a ground state to one short measurement, get like another signature. And then we do that polynomially often. And then we have polynomially many of these guys. And that allows us to extrapolate to what a signature of a state that we haven't seen yet, of a ground state that we haven't seen yet, would look like.
Right.
It's like an extrapolation model.
Right. Okay. And what is the values here? You're calculating a correlation function for this is
in the end, what we attempt is to produce one of these Monte Carlo approximations to a ground state we haven't seen yet. And the way we do that is we just do a convolution of all the classical shadows we have already seen and weigh them by a kernel function that takes into account the relation between the parameters that were associated with that particular training point and the classical parameters we're interested in now.
Mm-hmm. Okay.
So maybe in more traditional terms, we actually we use a Fourier ansatz. We first do a Fourier transformation of the density matrix and then try to approximate this Fourier transform by randomly sampled individual points and classical shadows thereof.
Right.
But we really try to, on a more high level, we take classical shadows of random selections and extrapolate them to produce a classical shadow of a ground state of a Hamiltonian that we haven't seen yet.
Right.
And then we can use this classical shadow to predict local properties, because that's what the theorem says.
Mm-hmm.
I'm sorry, I'm still a little bit confused because you say classical shadows, but I'm not really sure, like, is the shadow, like, what object is that actually? When you say shadow here, it is a selection of qubits, like a random selection of qubits, and the corresponding output you get from these measurements. That
it's exactly
the shadow.
Exactly, it's this guy. It has two things. It is a random matrix that combines two things. First, the random unitary transformation you chose to do, which is a classical source of randomness that kind of tells you that you kind of look into different directions. But the really important part is these computational basis outcome strings, because they're also random, but they carry the signature of the underlying quantum state. Because the distribution of these bit strings depends on the underlying quantum state. And so when I talk about classical shadow, I really mean a collection like this.
Okay, and in your case, the UIs, I mean, if it's just Pauli measurements random, then UIs would just be the rotations into that Pauli basis.
Exactly, or more extremely kind of like this is a tensor product and each single qubit state is pure and there are 6 possibilities. And that's kind of all you ever use. And this is what makes the procedure tractable on the classical level, because you only ever use tensor products of combinations of 6 possible single qubit states. But the underlying distribution still tells you something about the hidden density matrix, regardless of the correlations. And this is what ultimately drives the procedure.
Okay, thanks.
Can I ask, why do you call it classical?
Why we call it classical? That's a very, yeah, we started like after drinking some beers, we felt philosophical and we thought it's kind of, it's a bit like Plato's cave, and it's a classical, this object is purely classical. That's very important. It's kind of, this object is not a quantum state anymore. You can view it as a quantum state, but it's really just bits on your classical computer. And because they arise from randomized measurements that lead to a collapse of the wave function, it also, the randomized measurements let you view the density matrix from different perspectives. And in the end, give you some classical representation thereof, and we thought it would be smart or cool to call it shadows. But the classical part, I think, is important and justified. because it's all classical information. The important thing is that it comes from an underlying quantum experiment.
Okay, thank you.
What about a filter? Is it more like a filter, not a shadow?
Yeah, maybe we should have called it filter. we should have asked you before. So, kind of, there was a different motivation. Scott Aronson has his protocol on shadow tomography, right?
Yeah, yeah.
And this can be viewed as a tractable ansatz for shadow tomography also.
Yeah.
But yes, filter might have been better.
All right. So it seems that there are no more questions. So let's thank Richard again.